Good morning. We were talking about the chlor-alkali process, and we had almost completed it. But let me show you some very significant developments which you can actually quantify. If you look at it, continuous improvements in the chlor-alkali process have been going on for over a century. Even in the 1950s, the power requirement was something like 4,000 kilowatt hour per ton, which now has come down to about half, 2,500 kilowatt hour per ton. So it's a remarkable thing where engineers, especially, have played a very crucial role. They have been able to continuously strive for perfection of processes. It's not necessarily that a new process was invented, but whatever process existed, they could make it better and better. So at every point would appear that, yeah, everything is done. Okay? But you can see that every time someone has found a way of making it better. So, and this is no small feat to bring it down by close to about a factor of 2. And some of them I'd already mentioned about, like the advent of the dimensionally stable anodes in the 60s. That's why in the 50s it was much higher. But the moment those valve metal oxides coated on titanium were invented, that it made a huge difference because your carbon anode was not corroding anymore. It was a different anode. So that was very important. The second was that the diaphragm process, which was very popular in the 50s, that gave way to the mercury cell process, which was certainly more efficient than the diaphragm process. And the membrane process, as we found, I don't think you gain too much in energy, but it's more or less at par with the mercury cell process, which is again not bad. It's a significant achievement. Besides some of these major changes, there have been also constant improvements in cell design and operation. And you can imagine that today, with all the machinery and everything, you can fabricate things much more precisely. Precision engineering has improved. Anytime you can make things more precise, like for example, the distance between anode and cathode, obviously the power losses go down because the overall resistance of the cell goes down. So that's again another very important aspect. And the another, oh, it should be 4. Uh, is that, and we'll discuss this, there were certain integrations with fuel cell concepts, and so I'll talk about that. Another very important thing was that just like the anode was made dimensionally stable, we saw that the nickel catalyst is now used as the cathode. But even there, what people found is that if you can give a fine coating of platinum ruthenium over the nickel, that the overpotential reduces even further. So this is something which is being looked at. I think that everybody has not implemented it. If you see the article I sent, I think it was Johnson Matthey's article, you'll find a mention of this. We saw what is the cell potential. It is minus 2.19 volt. Okay, for generating hydrogen at the cathode and chlorine at the anode, and sodium hydroxide is obtained as a result. If I were to ask you, can you think of any other improvements, quite a drastic improvement that you might be able to make to bring down the cell potential? I've given the clue in the previous slide, but you can think about it. Okay, let's put it this way also, that the After all, we call it chlor-alkali cell. So the principal thing that we want is chlorine and sodium hydroxide. So I have again reinforced the clue. Now you can tell me. I'm sure you'll get the answer. As I told you, we are generating hydrogen, but that's because the cathodic reaction is forming hydrogen. This is where you can think quite smart and ask, do I have to generate hydrogen? Is there anything else I might do which is smarter? Because one thing you have to also remember that hydrogen is quite hazardous. Right? It can catch fire. I mean, it can have an explosive reaction. Okay, so I mean, if of course the objective is production of hydrogen, that's a different issue. But if you are just making hydrogen because you could not manage the electrolysis better, then obviously there is an opportunity for improvement. If I have generated hydrogen and suppose I've got oxygen, there is like a fuel cell, right? I can actually generate water from hydrogen and oxygen. Okay? You don't exactly do it that way, but what people do is that you can pump oxygen at the cathode, and now the reaction that takes place is not H plus going to hydrogen, but in presence of oxygen and 4 electrons, it forms hydroxyl ion. And look at the beauty. After all, hydroxyl ion is what I want to form, because that is what will react with your sodium ion and form sodium hydroxide. So I'm not forming any other thing which is unwelcome. I'm actually forming what I need to form. So now what happens is that I can make chloride to chlorine at the anode, and at the cathode I basically make hydroxyl ion. So effectively now the cell reaction becomes this. You can think of it as 2 NaCl plus half H2 plus H2O goes to 2 NaOH plus chlorine. Now this thing, you see, compared to the earlier one, whatever we saw under those alkaline pHs, to form hydrogen, you require something like minus 0.8 voltage, over here. Okay, over here, what happens is you actually gain energy. The cell potential over here is 0.40 volt. It's positive, means that it is a spontaneous process. Effectively, what happens is that now instead of minus 0.83, I'll write plus 0.4. So, you're talking about a voltage now which will drop to around 1 volt. Okay, you can see minus 0.96 volt. Now, that's a huge improvement over the minus 2.19 volt. Okay? And so, this is the kind of cleverness which you must try and always demonstrate. Okay, and it comes out of asking questions. Always this: why can't I do this? Why can't I do that? And so I've also put over here that if you look at the spirit of what you don't have can't leak, it's so beautiful because I'm not producing hydrogen. I don't have to worry about the safety of hydrogen. So not only does it actually save you a lot of power, I've also made the whole process far more safer by this. So if you see over here, that was the fourth point, that interfacing with fuel cell concept. And so it's not using H2 as a fuel, but basically effectively it's more or less the same thing. So this is the reason why the power has come down or can come down even further, if we do this. If you look at the thermodynamic cell potential, we saw it's minus 2.19 volt. It's 2.23. It's about that much. Okay. But actually, what we have to apply is not the thermodynamic potential. What you require is 3.46 volt. Of course, it will come down if we produce hydroxyl ion in place of hydrogen by pumping oxygen. But if I take the conventional process, it is about 3.46 volt, much higher. You're talking about extra 1.3 volt or so over and above the redox potential. Okay. Now, why does that happen? Because everything actually has an associated resistance. Okay. Your redox potential, etc., assumes an ideal situation where there is no cell resistance to look at, the internal cell resistance, but there is a positive internal cell resistance. Like, for example, your membrane is great, but don't forget it's not a metallic conductor or something. So there is a resistance which it offers, and it's something like 0.45 volt. The cathode, which I told you, the nickel cathode, even that offers a resistance of 0.35 volt. Electrolyte, the electrolyte also, because in some cases, in what is happening, that in one of the half cells, the NaCl is getting depleted. So the cell resistance will start increasing because of that. That's about 0.22 volt. Don't bother about structural IR loss. Anode overpotential, very low. The chloride to chlorine is done well in the dimensionally stable electrode. But overall, there is, if you add it all up, this comes to about 1.2 volts or thereabouts. And so that's the reason why it becomes 3.46 volt. Okay.
So what did you explain for electrolyte drop, sir?
Yeah. So, the electrolyte, obviously, when you have a lot of salts in it, you have a low electrolyte resistance. But if, let's say, suppose I take water as the solution, okay? Obviously, water will give you a very high resistance, right? Because there are no ions to transport the charge. What happens in the anode? In the anode, I am putting sodium chloride, but my chloride is going as chlorine, and my sodium ion is migrating towards my cathode to form sodium hydroxide. So what is happening is that anodic compartment is progressively getting more and more depleted in sodium chloride.
Yes, sir.
Okay, and so the resistance keeps going up.
Yes, sir. Got it, sir.
And so, of course, you allow it to reach a point, and that's when you will recycle and again resaturate the thing with more salt, and then again put it back. You have to allow it to happen for some time, and then only do that process. Okay? So is this part also clear to everyone? All of you understood that how
Yeah.
the cell
Yes, sir.
potential is going down? Okay. Now, let me ask you, we have talked about, of course, three ways of making sodium hydroxide: the diaphragm cell, the mercury cell, and the membrane cell. Now, starting from NaCl, is there any other way possible? Actually, we have covered it before. You just have to recollect. One, of course, we discussed, no, but that's from sodium carbonate, how you can make sodium hydroxide. I'm not talking about that. I'm talking about from NaCl. I think when we were talking about sulfuric acid, we had mentioned this, but I'll still look at it in the context of sodium hydroxide production. That this is a very interesting process, which is bipolar electrodialysis. So effectively what happens in this is that there are three kinds of membranes. One is a cation exchange membrane, one is an anion exchange membrane, and one is known as the bipolar membrane. It's a sandwich membrane of an anion and cation exchange membrane. And what happens is that in this membrane, in this interface, through the application of a potential, it's still an electrically driven process. You can split water into H plus and OH minus. I mean, when I say split water, it means go way beyond the conventional dissociation constants. I mean, you can make copious amounts of H plus and OH minus from water, far more than the dissociation constant. Now, what happens is that, let's say over here, say I'm passing my feed salt solution, let's say sodium chloride. Now, so what will happen is that this is an anion exchange membrane, so it only allows anions to pass through, but blocks of the cation. So my anion passes this way, and bipolar membrane is generating H plus. So what is happening is that this H plus and this anion, which is chloride, becomes HCl. Likewise here, I can think of, let's say, passing feed solution like sodium chloride also through here as well as here. Now, what happens is that over here, this is the anode. So in the anode, my, let's say, chloride is going to chlorine. Now my sodium ion is permeating. It's not very different from the membrane process. It's permeating this way, and my OH minus from here is coming here. So here I form NaOH. So effectively, in the bipolar electrodialysis process, I simultaneously regenerate acid and alkali from the salt. So a lot of people actually practice it. Like if people want both acid as well as alkali, suppose you say that I want to produce sodium hydroxide plus hydrochloric acid from sodium chloride, then this is not a bad way to do it. So this is what you'll end up with. Like this is a plant, you can see in China, it's a massive plant producing something like 4 lakh tons of sodium hydroxide by bipolar membrane. There are variants of the bipolar membrane. Like for example, suppose I'm passing sodium chloride and I've got an anion and cation exchange membrane. I don't have that sandwich membrane in between. Now from one side I pass hydrogen, and the hydrogen becomes H plus. So it's getting oxidized. And I'm passing sodium chloride from here. The chloride is moving in this direction. So what happens is that it's moving in the direction of the anode. So effectively, what's happening is that this cell, I'll end up having HCl, and this sodium ion cannot migrate through the anion exchange membrane, but it can pass through the cation exchange membrane. So the sodium ion goes this way, and over here, like if I've got NaOH, which is being formed, in other words, my water, you can think of as if the H plus is becoming hydrogen, and this is becoming NaOH. So effectively, this cell becomes depleted in sodium chloride, and this cell becomes concentrated in HCl, and this cell becomes concentrated in NaOH. You can get a concentration of up to about 20% acid and alkali with this kind of methodology, which is okay. In many cases, it's fine. And especially if you have got base salts, like some effluent, which has got sodium chloride, etc., it's a very good method to think about this kind of acid and alkali, which you can get from a effluent. Now we are through with caustic soda chlorine as well as soda ash. I thought that let me cover one more very important production which is related to electrolysis, and that's the production of aluminium. Okay? And I think all of you have learned it. How do you produce aluminium? What process? Have you heard of the Hall-Heroult process?
Yes, sir.
Yes, sir.
If you look at the production of aluminium, like let's say I've taken 2018 data for the whole year, you can see that in the world, something like 64 million tons of aluminium was produced in 2018. There's such a huge gap between one country and all the rest. and that country is China. You can see how much they have produced and how much the rest of the world has produced. In other words, they have produced something like half of what the whole world has produced. 50% has been produced in China. Now, this is again important. It's not just in aluminium. You'll find this across the board, in many different productions that the Chinese have leaped ahead, way ahead of everybody else. In the last, especially, I will say, 40 years, they have really done an amazing job of constantly improving their processes. That's one, and also producing at scale. I mean, that they can conceive of scales, of production which earlier probably only countries like the United States thought they could do, but the Chinese today have been able to do that. So it is scale plus, and there has been today, if you look at publications, patent literature, whatever you want to look at, you'll find that it's dominated by the Chinese. I mean, so they have really invested massively in their science and technology infrastructure. Why did aluminium become so important? What are the important properties of aluminium?
So it is light.
Absolutely. I think that is the singular most important property, that it is lightweight. There are so many aeroplane parts. Today, if you look at the wheels, they will all be lightweight because of aluminium. And not just aluminium, there are alloys between magnesium, another lightweight metal, magnesium and aluminium. So those are the kinds of things which have really led to a huge improvement in the efficiencies of transportation because of progressive introduction of aluminium. So many utensils also were aluminium based. Okay. Now there is another property of aluminium which actually makes it very attractive. Can someone tell me what it is?
So very malleable.
Yeah, malleable. Of course, most metals are malleable. I mean, it's an advantage. What happens is that aluminium tends to form a very fine layer of alumina. And so what happens is that it can cut off further corrosion because you have formed an insulating layer. And this is the property of many things, not just alumina, but even silicon. It will form a fine silicon oxide layer, which is very useful, for example, in photovoltaic cells, that it gives a stability to the bulk of the material. Otherwise, the whole thing will progressively corrode. So that's another protective alumina layer, and as you said, malleable. Okay, so you can look up, all the properties of aluminium, and aluminium also is a fairly inexpensive metal. It wasn't like this before, but today aluminium is very affordable as a metal. So bear that in mind also. And you would have learned that the Hall-Heroult process is the method by which production has been taking place. It's very interesting. All of this, like we saw the Kastner-Kellner cell. Kastner and Kellner were the bitterest of competitors, enemies, but they joined hands. For a long time, Hall and Heroult were actually fighting a battle. One of them was French and one was American. and they were fighting a battle as to who invented this process. And finally, it was a stalemate, and they decided to join hands. And so that's how we have the Hall-Heroult process. Can you remember something about the Hall-Heroult process? Actually, what happens?
Sir, we take bauxite.
Yeah, wonderful. Very good. Excellent. So the first thing you have said, take bauxite. And then
Sir, treat with caustic soda, I think.
uh,
I mean,
you mean, yeah, you are talking about finally you will make alumina from bauxite. Is that what you're saying?
yes, sir.
Ah, okay. Take bauxite, make alumina from bauxite. And then what happens after that? Very nice.
Sir, then we make it to aluminum hydroxide, ALOH3.
You make it to aluminium hydroxide. But let's put it down. Aluminium hydroxide and then from it dot. Okay.
So you reduce it to aluminium by using carbon electrolytically.
Wonderful. Reduce alumina with carbon.
Yes, sir.
With carbon. And how would you do that?
So electrolysis.
Yeah. So how would you do the electrolysis?
So using molten alumina and using carbon as the anode.
How wonderful. Molten alumina and carbon as anode. And so what happens to the carbon?
So it becomes CO2. You have to keep replacing the anode.
Terrific. Terrific. Very good. Very good. You're almost there. I mean, there's nothing for me to teach, but let me still take you through some of the nuances. It's a really one of the marvels of technology. Conceptually, of course, what you have said is right, but if you look at the details are very interesting, and I think it's really commendable that you have very clearly said that the overall cell reaction that is taking place is alumina plus carbon going to aluminium plus CO2. Now, one could have said, because there are so many other metal oxides which you can actually reduce to metal, right? We know that. For example, starting from iron oxide, I mean, I can make it iron. I don't do it by electrolysis. I do it by actually taking carbon and at a high temperature, it forms CO and CO2 and it forms metal. Now the question is, why can I not do the same thing with alumina? You understood the question, huh?
So it doesn't melt very easily, probably.
That's one reason. That's a important reason.
Sir, it is
No,
spontaneous at low temperature, as a relatively low temperature.
this is very interesting. That let us put it down, spontaneous or non-spontaneous. Okay. Now what happens is that the aluminium oxygen bond is so strong that you cannot form aluminium and CO2. It is not a favored reaction. This reaction will not go thermodynamically even if you try. So you will require an additional source of energy. And in a way, It is the electrolysis process that supplies that energy. You are carrying out this reaction, but you are not generating power from the Hall-Heroult process. I have to actually have a power input. In other words, this plus a power input is making the whole thing favored, and it's taking place. So now let us look at what are some of the very, very important things that have been done in this particular process. Conceptually, as you said, the anode is a sacrificial carbon. Now, let me ask you also, why was the anode made a sacrificial carbon? Well, I mean, like, could I have used a dimensionally stable anode like in the chlor-alkali process? Why did I need to do this? Any idea? Why did you want a sacrificial anode? You see, the reason is that although it is non-spontaneous, but the fact is that I gain so much energy from carbon becoming carbon dioxide that it helps to offset my overall cell potential. Otherwise, if I had some other reaction and all, your overall cell potential would be extremely high. The power consumption would be extremely high. So it's much better that you sacrifice carbon, which is a relatively cheap material. And the kind of carbon that is used over here are things like pitch blend and things like that. You don't use graphite as your electrode. Just bear that in mind. Now, the other very interesting thing is that what you have is, although and aluminium, exactly as you said, that it melts at a very high temperature, but I could reach those temperatures by the electric arc furnace. I could do that, and the temperature is brought down to under 1,000 degrees, and that was the great work done by Hall and Heroult. That they were able to identify cryolite, Na3AlF6, okay, as one of the substances which interacts with alumina, okay, and it is not just a simple dissolution. Okay? Like people say, it reduces the dissolution temperature, but it is a reactive dissolution, and we'll see that. So that's very interesting that that cryolite does that, and not that cryolite actually plays several roles in this whole process, and we will have a look at that. What are all the roles that cryolite plays? It plays at least 5 to 6 roles. Okay? It's one of the most incredible inventions. How creative the way they have done this. So what is the process? Let us try and understand. This is your anode, which is sacrificial carbon, as you have said. The cathode is again a carbon, and it is in the form of a boat. Like this is your cathode. Okay? Obviously, at the cathode, you are forming aluminium, and under the temperatures in the cell, the aluminium is in a molten form. Keep that in mind. Melting temperature of aluminium, 660 degrees. Melting point 660 C. So under those conditions, the aluminium forms a liquid. It's interesting, although we say a graphite electrode, moment I've got aluminium sitting over the graphite, it's a moot point as to what is the electrode. The electrode for subsequent reduction of aluminium will obviously be the aluminium itself. It will serve as the electrode. Now, what then happens is that I put in alumina in the presence of the cryolite. It gets molten at a temperature of around 950 degrees C. And so my cryolite is also molten. The whole thing is molten, and my aluminium is like a separate phase in a molten form. In the anode, the reaction that is taking place is really between the oxygens of alumina and the carbon, that it is forming CO2 and stripping off electrons. And those electrons are now going towards the cathode. And that's where your reduction of this aluminium ion to aluminium is taking place. But you will see soon that it is not a simple naked Al3 plus. It's more complicated than that. Okay, let me ask you another thing. I need a temperature of 970 degrees centigrade. How is this cell being heated? How are you heating up the cell? What would you do? Now, this is quite interesting. We have seen, even when you saw the chlor-alkali process, you saw many cases where there was an IR drop. Means because there is a cell resistance and because current is flowing, you will generate a lot of heat, right? I squared R is energy, heat I'll generate. Okay? Now, in the Hall-Heroult process, what they do is they apply a fairly large potential of about 5 to 6 volts and a huge current. It's operated at extremely high current densities. Now, because the cell resistance is quite high, especially because although we say cryolite is an electrolyte, but it's not a great electrolyte. So it offers considerable cell resistance. So with such a high cell resistance plus the very high current, so my I squared R term is extremely high. So high that I can actually heat up my cell to this temperature. And so the heating of the cell to the temperature is a natural consequence of the I squared R or the ohmic losses. So it's not as if the entire ohmic loss is a wasted effort. It's not. They have used it very intelligently. Of course, if you ask me, it's not the wisest thing to take the highest form of energy, which is electricity, power, and convert it into heat. It's like running our geyser, right? And generating hot water. I mean, it's a stupid thing to do. Not the wisest, but under the circumstance, to maintain a very high production of aluminium, I need a high current density. And they said, I need a high temperature. Why should I apply heat from outside? Let me get the heat from the ohmic losses of the cell. Is it clear to everyone? Understood? Now, another thing that you need to understand is that you are charging alumina from a silo inside this cell. That's your alumina going in. Now, if you do not, if there is a depletion of alumina for whatever reason, then what will happen is that you still have cryolite. Don't forget, I've got Na3Al So I have things which can potentially get oxidized. So, for example, my carbon, I might form other forms of carbon through an oxidation process. I've got cryolite has got fluoride in it, Na3Al. What can happen is that that fluoride can become fluorine, at the anode, and then strip off hydrogen from my pitch blend, because my pitch blend is what? It's not absolutely pure carbon. There is some hydrogen. So obviously the fluorine will react with the hydrogen, and I may get release of things like HF. So there can be competing reactions which I have to take care of. So I need a gas scrubber, before I let things out, because there are volatiles, and you'll see even aluminium fluoride, is volatile under those conditions, and some amount of aluminium fluoride is lost in the process. also keep that in mind. Let us try and understand the various requirements that are fulfilled by the cryolite bath. One of the most important, of course, is that it must be molten under these conditions. It has a density which is so low that it floats over the aluminium. And why that is required is that it prevents the aluminium from getting oxidized at the anode. Because it can happen under those conditions. You are through a hopper, you are putting things, there can be a splash of aluminium. And so if that happens, there will be a disaster, because obviously aluminium will get reoxidized to Al3 plus at the anode much more easily. So the cryolite, it just goes and floats over it and prevents that reaction. It's of course a solvent for alumina, but it's a reactive solvent. Okay? It ionizes and conducts electricity, though not so well. Okay? And it is relatively not so volatile, but you still do lose AlF3. So you start with Na3AlF6. I can express it as NaF plus AlF3, and some AlF3 volatilizes in this whole process. Now, this I may not have the time to go through in detail, but I want you to read it. Interesting thing is that the alumina reacts with cryolite and forms these kinds of species. So these are the species that actually participate at the anode and the cathode. It is not Al2O3. So remember, it's actually an anionic species that is going towards the anode and is getting oxidized there and is forming CO2. And at the cathode also, it is the AlF6 3-. So you can think of it as if it is the cryolite which is getting reduced to aluminium. So there is an interplay between the cryolite and the alumina. They together form one composite kind of a system with many different constituents. And so the reaction that is taking place at the cathode is cryolite. And that's how, also when I'm releasing fluoride, that fluoride can get oxidized at the anode. So that will be a competing reaction. So I have to be very careful to prevent it. So those are the subtleties of the whole process, and you must understand that there are many competing reactions. Just like we did in the chlor-alkali process, you can see where your potential drops are occurring. Why is it that even though I have got a cell voltage which is something like 1.18 volt, why is it that I have to apply 4.3 volt? So what are the contributions to the cell potential, which are the overpotentials? You can see massive ion drop across the electrolyte. So forget about cryolite being a great electrolyte. It isn't. There's a huge resistance in the electrolyte. The electrodes offer huge resistance. And all of this basically leads to a very high overall potential of around 4.3 volts, whereas the thermodynamic potential is about 1.18 volt. And coupled with that is the massive current density at which the cell is operated, and that's what is generating huge amounts of I squared R, heat, which is forming and heating up the cell. Is that clear to everyone?
Yes, sir.
Okay, thank you. All the best.